Hello everyone, welcome to the Mercury Virtual. Hope you are doing good. Today I am going to continue with your same module, that is the database design concepts, and the same chapter, that is chapter number 6, that is the formal relational query languages. That is what are the various formal relational query languages and what the role of. So this is the select, that is how to use the select, that is whenever we want to give the condition that is given in the select clause or that is given in the select statement. This is represented by the sigma, that is the select department name equals to physics. So find the names of all the instructors who have a department name that is of physics, that is from the instructor table. Always the relation table is given in the parenthesis, that is given in the brackets. So this is it shows the tuples of the instructor relation where the instructor is in the physics department. So whenever I want to find anything, the relation or the table is given in the bracket, that is the parenthesis, and we can say the condition that is given by the select operation. Right. Now this is another, that is also example that we have discussed, that is salary is greater than 90,000. In general, we allows comparisons using the equals to, not equals to, less than equals to, greater than equals to in the selection predicate. So in general, in comparison, we use the, or we allow the comparison using the various symbols like equals to, not equals to, less than, greater than, less than, equals to. Furthermore, we can also combine the various operations, various operator that is also used. So we can combine the equals to, not equals to, less than, equals to, less than equals to using the connectors, using the, we can say, the comparison operators, that is a connectives, that is operator used, that is a union, intersection and the not. Therefore, to find the instructor in the physics with the salary greater than the 90,000, we can write. So now I want to find the department name equals to physics as well as the salary that is greater than the 90,000. That is, both the conditions are combined together. That is, the department is physics and the salary is also greater than the 90,000. That is given using this one. The selection predicate may include comparison between two attributes. To illustrate, consider the relation department to find all the department whose name is same as the building name. So whatever the name of the building, whatever the department name that is given, that is a building name, that is a department name equals to building, that is a department. This is the condition that we have discussed. Then we have discussed what are the difference between the SQL and the relational algebra. Then we have discussed about the projection. So if I want to display the number of rows, number of column, number of different operation that is performed, that is done by the project operation. So suppose we want to list all the instructor ID, name and salary, but do not care about the department name. The project statement or the project condition operation allows us to produce this relation. So it's a unary operation that returns its argument relation with certain attributes left out. Since a relation is a set, any duplicate rows are eliminated. So relation is a set, so any duplicate rows that is represented are duplicated in this one. So, and it is denoted by the pi sign, and the selection is denoted by the sigma sign, while the projection is denoted by the pi sign. In select or in selection we use the condition, but in, we can say, the projection, we simply produce the relationship, we simply produce the tuple that is used. So we list those attributes that we wish to appear in the result as a subscript to the pi. So it is also used in the subscript. And figure 6.3 shows the relation that results from this query. Then next is the composition of relational operation. That is, what are the various components, or what are the various composition, or how to find out the query that is in a combination of the we can say that is in the combination of the relational operation, that is the selection projection. So this is a combination composition of the selection and the projection. Notice that instead of giving the names of the relation as the argument of the projection operation, we give an expression that evaluates to a relation. So there is a relational algebra expression that is considering the relational algebra, that is the selection operation, projection operation. Then next is the union operation that is used, that is how to find the union operation. So consider a query to find the set of all courses that is taught in the fall 2009 semester, the spring 2010 semester or both. That is, consider a query that in which we want to find that both the spring and the fall season are used together, as well as the different year, that is the fall 2009 semester, spring 2010 semester, or both 2009 or 2010 along with the fall and the spring. The information is contained in the section relation. To find the set of all courses that is taught in the fall 2009 semester, we write that is a pi, then there is a course ID, then there is a sigma, then semester equals to 4 and the year equal to 2009. So that is a pi, then course ID, and that is finding the or displaying the course ID, that is a course ID of the course. Then there is a sigma, that is a select, semester equals to 4, that is a finding all those tuples or those relation where the semester equals to 4 and the year equal to 2009, and that is represented by the relation that is a section. And to find the set of all courses that is taught in the spring 2009 10 semester, then we write that pi course ID, then sigma semester equals to spring and the year equals to 2009, that is a section. To answer the query, we need the union. So we need the union, that is the union, that is the two sets that is also needed. So this is the course ID, section ID, semester, year, building, room number, time slot ID. This is a course offered by the either 9 or 2009 and the spring 2010 or both the semesters. Then we will discuss what are the various attributes to composite, or what are the various attributes that is used for the union operations. So two conditions must be satisfied, that is the relation or the, we can say, there are two relations, that is the R and the S, and if I want to find the union among the R and S, so the relations R and S must be of the same arity, that is they have the same number of attributes. If first relation, first table have 4 attributes, that is the 4 columns, and the second table must also have the 4 attributes to be combined together. Then the domains of the ith attribute of R and the ith attribute of S must be the same for all i's. Note that the R and S can be either database relation or temporary relation that are the result of the relational algebra expressions. Then next is set difference operation. That is, if I want to find the relations that is contained in one relation, if I want to find out the tuple that is contained in one relation but not in the another relation, that is represented by the set difference, that is represented by the minus sign. So this allows us to find the tuples that are in one relation but not in the another relation. The expression R minus S produces a relation containing the tuples in R but not in the S, that is the R minus S. That is finding those tuples that are in R but not in the S. That is a set difference operation. Now next is the Cartesian product operation, that is today's topic, that is how to multiply two relations or how to find out the product of two relations. The Cartesian product operation, that is denoted by the cross sign, allows us to combine information from any two relations. So if I want to find out the or combine the information from two relations, that is denoted by the multiply sign, that is denoted by the Cartesian product operation. We write the Cartesian product of relations R1 and the R2 as R1 into R2. So we find the Cartesian product of relations R1 and the R2, that is denoted by the R1 and the R2, that is the R1 into R2. Recall that a relation is by definition a subset of a Cartesian product of a set of domains. From that definition, we should already or we have already defined an institution, that is how to find the relation or what are the various domains that is available in the relation, or what is the relationship between the subset of a Cartesian product. However, since the same attribute name may appear in both R1 and the R2, suppose there are same attributes, there are same relation that is available, same column that is available in both the R1 and the R2. So R1 is a one relation, R2 is a another relation, another table. So if the same attribute may appear in the both the relation, then we need to devise a naming schema to differentiate between these attributes. So we are using the naming schema, or we are giving the different names to the different attribute. We do so here by attaching to an attribute the name of the relation from which the attribute originally came. For example, the relation schema for R, that is equals to instructor into teaches. That is a two tables are combined, two tables are mixed come together. One is the instructor table, one is the teaches table. So what is the relation schema among these? That is the instructor.id, instructor.name, instructor.department name, instructor.salary. So one is an ID, one is a name, one is a department name, one is a salary. There are four fields, there are four attributes that is combined with the, or that is fetched with the instructor table. Then there are again the four or five attribute, that is ID, that is a teacher's ID, teacher's course ID, teacher's section ID, then teacher's semester, then teaches year. So these are the five attributes that are also taken from the table, that is a teaches. So four attribute is taken from the table instructor, and the five attributes is taken from the table teaches. With this schema, we can differentiate the instructor.id from the teaches.id. So there is a difference between the instructor.id and the teaches.id. For those attributes that appears in only one of the two schemas. So for those attributes that is available in both the schemas, on any one of the two schemas, we shall usually drop the relation name prefix. So if I want to apply or if I want to modify them, that is if I want to find out the attribute that appears in only one of the two schemas, that is there is a relation or there is an attribute that appears in any one of the two schemas, any one of the two tables, we must drop the, or we usually drop the relation name or relationship name prefix. This simplification does not lead to the ambiguity. We can write the relation schema for the R as follows. So if I want to find out the attribute that have a same name with the two schemas, then we usually drop the relation name prefix. This is instructor.id, name, department name, salary. That is only one time the instructor table name will be used, that is used as the prefix name. So this is the instructor.id, name, department name, salary. So there are four fields that is available from the instructor, that is taken from the instructor, that is ID, that is a name, name of the instructor, department name of the instructor, and the salary of the instructor. In the same way, there is a teaches, that is a teaches.id, course ID, section ID, semester, year. This naming convention requires that the relation that are the arguments of the Cartesian product have distinct names. This requirement causes problem in such cases, such as when the Cartesian product of a relation with itself is desired. A similar problem arises if we use the result of a relational algebra expression in a Cartesian product. Since we shall need a name for the relation, so that we can refer to the relation attribute. In section 6.1.7, we see how to avoid this problem by using the rename operation. So there is also difficulty of the renaming operation. So if I multiply we can say if I multiply the two words, if I multiply the two attributes of the different rows, that is the one attribute is multiplied by another attribute, so that gives a problem of the naming convention. So the ID is matching with the ID and the name, then there is a course ID, then there is a section ID, there is a semester, there is a year. That is the teacher's relation. Now, note that we know the relation schema, that is R equals to instructor.teaches. So what tuples appears in the R? What kind of tuples, or we can say what type of rows that is appears in the R? That is the R means what is the output of the combination of the two tables? So as you may suspect, we construct a tuple of R out of for each possible pair of tuples. One for the instructor table, that is from the 6.1, and one for the teaches table, that is given in this one, that is figure 6.7. This is the table that is given, right? Therefore, R is a large relation because it contains both the values, or it contains the values of both the relation, that is the instructor and the teaches. So R is a large relation, as you can see from figure 6.8, which includes only a portion of the tuple that makes up R. That is used for the R, that is the instructor is multiplied by the teaches. Assume that we have n1 tuples in instructor and n2 tuples in teaches. Then there are n1 into n2 way of choosing a pair of tuples. So if there are two tuples, if there are, we can say the n number of tuple or n1 tuples of the instructor as well as the n1 n2 tuples in the teaches, therefore n1 into n2 is used for choosing a pair of tuples, that is one tuple from each relation. So there are n1 into n2 tuples in R. In particular, note that for some tuple t in R, it may be used that t instructor ID is not equals to t teaches ID. So in some cases, we also note that the some instructor is also used for the instructor.id and the teachers.id. In general, if we have the relations, that is the R1 R1 and the R2 R2, then R1 into R2 is a relation whose schema is concatenation of the R1 and the R2. So this is just a multiply, that how to use the multiply between them. This is the figure 6.8, that is the result of the instructor and the teaches. This is the instructor ID, name, department name, salary. This is the teaches ID, course ID, section ID, semester, year. So all the four fields of the instructor table is also available over here. All the four fields of the teaches table is also available over here. That is the result of the instructor and the teaches. Note that we rename the instructor.id as the inst ID to reduce the width of the table, nothing else. So if I multiply two relation, that is R1 into R2, that is a concatenation of the R1 and the R2. Relation R contains all tuple T for which there is a tuple T1 in the R1 and tuple T2 in the R2, for which TR1 equals to T1 R1 and the TR2 equals to T2 R2. Suppose that if we want to find the name of all the instructor in the physics department together with the course ID of all the courses that they taught. So suppose if I want to find the names of all the instructors that have a physics department that is available in the physics department with the course ID of the relation that we taught. So we find the information in both the semester or instructor relation and the teacher relation to do so. If we write sigma department name equals to physics, that is finding the department name that is equals to physics from the two tables. How I know there are two tables? Because this is the multiply sign, that is the instructor into table or teaches. And this relation is available in figure 6.9. So there is a figure that is 6.9, that is a result of the finding the physics department name equals to physics from the two tables, that is instructor and the teaches. So this is the department that is physics that is available from the instructor and the teaches. We have a relation that pertains only to instructors in the physics department. Therefore, the course ID column may contain information about the courses that were not taught by the corresponding instructor. So there are some instructor, there are some relation that is also available for containing the information that is not available for the corresponding instructor, that is how to use the instructor and what are the purpose of using the instructors. Since the Cartesian product operation associates every tuple of instructor, that is since it associates or it deals with every tuple of instructor and with every tuple of teaches, we know that if instructor in the physics department have a course, then there is something, that is some department, there is some tuple that is equals to this one that contains his name, which satisfy the instructor.id equals to teachers.id. So if we write instructor.id that is equals to teachers.id, then department name equals to physics, instructor into teaches. Then we get only those tuples of instructor that pertains to the instructor in the physics and the courses that they taught. Finally, since we only want the name of all the instructor that is used in the physics department together with the course ID of the courses that they taught, we do a projection. So finally, since we need only want the right or names of all the instructor in the physics department, that they taught with the course ID of all the courses that they taught, we do a projection. That is a how to apply the projection. That is a projection operation. That is the project name, course ID, and select the instructor.id equals to teachers.id. That is the department name equals to physics and instructor into teachers. The result of this expression that is also available, that is shown in the figure 6.10. This is the result of this one. That is the finding the name and the course ID. Condition is that instructor ID and the course ID is similar. And one more condition, that the department name equals to physics from the two tables. Now look, instructor ID is equals to the course ID in this physics department, right? There are two, that is same. This is not same, this is not same. So this is instant physics 101. That is this is on the only the same, that is this is same, this is same, so this is only one row that is available, that is physics 101. Now next is the rename operation. So we have covered with that one, that is a Cartesian product operation. That is how to multiply two tables, that is both the attributes of the one table must be combined with both the attributes of the another table. That is a Cartesian product operation. Now next is the rename operation, that is how to find the rename operation or how to do the rename operation. Rename operation, that is how to do the rename or how to do the rename of the relation, how to do the rename of the different relations, that is the rename operation. So we have covered with the Cartesian product, set difference, select projection operation. Now next is the rename operation. So unlike relations in the database, that is unlike tables in the database, the results of the relation algebra expression do not have a name that is used or that we can use to refer to them. It is useful to be able to give their names. The rename operator, that is denoted by the lower case Greek word RHO, that is phi. Let us do this. Given a relational algebra expression E, the expression is PXE, that returns the result of the expression E under the name X. A relation R by itself is considered as a trivial relational algebra expression. Therefore, we can also apply the rename operation to get a relation R to get the same relation under any new name. So we can apply the new name, we can give the new name by using the rename operation, that is denoted by the phi. Our second form of the rename operation is as follows. Assume that the relational algebra expression E has a artery, that is the n, that is a number of attributes, that is a number. Therefore, the expression, that is Px a1 a2 an E, that returns the result of the expression E under the name X, and which the attribute and with the attributes renamed to the a1 a2 a3. So there are different attributes that is available, that is a1 a2 till an, and there is an expression that is the E. To illustrate the renaming relation, we consider the query, find the highest salary in the university. Our strategy is to compute a temporary relation consisting of salary that are not the largest, and then take the set difference between the relation, that is a pi salary instructor, and the temporary relation just computed to obtain the result. Now what is the step 1? To compute the temporary relation, we need to compare the values of all the salary. So if I want to compare the value of all the salary, we do this by comparison operator by computing the Cartesian product of the instructor and the instructor. So we are finding the Cartesian product of the two tables, that is the instructor into instructor, and forming a section to compare the value of any two salaries appear in one tuple. So if we are able to find the salary that is appear in one table, that we can do in the first step. First we need to devise a mechanism to differentiate between the two salary attributes. We shall use the rename operation to rename one reference to the instructor relation. Therefore, we can reference the relation twice without any ambiguity. That is step 1. This is the salary. That is the result of the sub-expression. That is whatever the result that is given. That is the result of the sub-expression. That is a pi instructor dot salary. Then what is the, we can say, the select operation. What is the condition? That is the instructor dot salary is less than d dot salary is and the instructor into pd instructor. Now we can now write the temporary relation that consists of the salary that are not the largest. That is the instructor dot salary. Then instructor dot salary is greater than or less than d dot salary. Then instructor into pd instructor. So whatever the value, whatever the, we can say, the demand, whatever the expression that is given, that is denoted by the p. This expression gives those salary in the instructor relation for which a last salary appears somewhere in the instructor relation. The result contains all the salary except the largest one. So result contains all the salary that is available except the largest one. Figure 6 point show one display the output of this expression. Now what is the step 2? The query to find the largest salary in the university can be written as. So whatever the query that is given to find the salary of the largest salary in the university, we can write as phi or pi salary instructor, then the pi instructor dot salary. What is the condition? That is the instructor dot salary is less than d dot salary and instructor into pd instructor. So the two relations or the same relations will be combined together, that is the instructor into instructor. So figure 6.12 shows the result of this query, whatever the query or whatever the result of this query. That is salary is 95,000. That is finding the maximum salary that is available, that is the instructor into instructor, that is the instructor dot salary is less than d dot salary. So the rename operation is not strictly required. Since it is possible to use a positional notation for attributes, we can name the attributes of relation implicitly by using a positional notation. So there is a positional notation that is given where $1 and $2 refers to the first attribute, the second attribute, and so on. So if I given $1, that is the first attribute, the first column, second column, and the third column. So if I use the positional notation, that is $4, that is the second fourth attribute, and the fourth attribute is compared with the eighth attribute that is given. So the 4 attribute, that is a salary attribute, that is the first occurrence, that is a $8, that is the eighth attribute, that is for the second occurrence of the instructor. Now this is also over, that is how to rename, that is also over. Now next is the formal definition of the relational algebra. That is, what is the formal definition, how to use the relational algebra. So the operations in section 6.1.1 allows us to give us complete definition of an expression in the relational algebra. A basic expression in the relational algebra consists of either one of the following. So a basic expression that is given in the relational algebra can be given as follows. Can be contained or can be divided into following categories. That is, first is a relation in the database, second is the constraint or constant relation. So one is the relation, whatever the table that is used in the database, and next is the constraint relation. A constant relation is written by listing its tuple within the braces. For example, 2 to 2, Einstein, physics, 95,000. This one, this one, this one. A general expression in the relational algebra is constructed out of the smaller sub-expressions. Let E1 and E2 are the relational algebra expression. Then the following are the relational algebra expressions. These are the relational algebra expressions. That is the E1 union E2, E1 minus E2, E1 into E2. This is the pi, that is pi is a predicate, then there is a sigma, then this is a pi, then this is a rename operation. Now what are the additional relational algebra operation? That is except that the basic operation, there is an additional operation that are as follows. So what are the various addition relational algebra operation that is also available in the relational algebra? So there are multiple additional operations that is as follows. So the fundamental operations are sufficient to express any relational algebra query. That is a fundamental operation that is available are more than sufficient to express the relational algebra query. However, if we restrict ourselves to just the fundamental operations, certain common queries are lengthy to express. So there are certain queries which are very lengthy to express. Therefore, we define the additional operations that do not add any part to the algebra. Therefore, we can add or we can define additional operation that will be added or that we cannot or that do not add to any part or any part to the algebra. But simplify common queries. For new operations, we need or we just give an equivalent expression that uses only the fundamental operation. That is, what are the various fundamental operations? What are the various, we can say, the approaches that is used with the fundamental operations. So this is the output, that is course offered in both the fall 2009 and the spring 2010 semester. So this is the courses that is offered by both the semester, by both the years, that is the fall 2009 and the spring 2010 semester. So first of the operation, one of the additional operation that is available in the set intersection operation. So this is the first additional relational algebra operation that we shall define is a set intersection operation, that is denoted by the reverse U. Suppose we wish to find the set of all the courses that is taught in the both the fall 2009 and the spring 2010 semesters. Using set intersection, we can write pi course ID, and what is the, we can say, the condition that is required, that is the semester equals to 4 and the year equals to 2009, and it is available as a section, that is it is available, or it is given the, or it is giving the expression, it is giving the argument, it is giving the table name as a section. So this is the pi that is giving the display the results, and we can say the course ID, then semester equals to 4 and the year equal to 2009, and there is a section. Section means the name of the table. Then again the pi, then course ID, then semester equal to spring and the year equal to 2010. Then there is also a section part, and there is a union, or we can say that there is a set intersection that is available between these, that is denoted by this one. So first of all, find this one, then find this one, and there is an intersection, that is a set intersection in between this one. The result notation for this query that is appears in the figure 6.13. Note that we can rewrite any relational algebra expression that uses set intersection by replacing the intersection operation with the pair of set difference operation, that is as follows. So whenever we use the R set intersection S, that is equals to the R minus S. Therefore, set intersection is not a fundamental operation and does not add any part to the relational algebra. It is simply more convenient to write RS than to write R minus S. That is, it is very better, or it is simple to write the R set intersection S as compared to the write R minus S. Right. Next is the additional operation that is used is the natural join operation. So one is the set intersection operation, that is the additional operation that is available in the relational algebra query. Next is the natural join operation. So it is often desirable to simplify certain queries that requires a Cartesian product. Usually a query that involves a Cartesian product involves a selection operation on the result of the Cartesian product. So whatever the Cartesian product that is available, that is a major expression, that is a given expression that is available in the Cartesian product. The selection operation most often require that all the attributes that are common to the relations that are involved in the Cartesian product be equated. In our example, that we combine information from the instructor and the teachers table, the matching condition requires instructor.id to be equals to the teachers.id. These are only attributes that is given in the two relations that have the same name. So every two attributes that is given that have the same name. The natural join is a binary operation that allows us to combine certain selections and thus Cartesian product into one operation. That is a natural join. It is denoted by the join symbol, that is, this is the join symbol that is available. That is a natural join. The natural join operation forms a Cartesian product of its two arguments. That is, the natural join performs the same operation that is done by the Cartesian product, and it is denoted by like a we can say it is denoted by the two arrows, that is like a dumb rule that is available in this one. So the natural join is related with this one, that is, the joins the two relation, that is the instructor table as well as the teachers table. This is the ID, this is the name, department name, salary, then course ID, section ID, semester, year. This is the natural join of the two instructor relation with the teachers relation. This is again the notation that is used with the instructor table, that is used with the, we can say, the natural join that is available. Then next is the assignment operation. So one is the set intersection, one is the natural join, next is the assignment operation, that is how to assign the values, how to assign the, we can say, the denote the values, passes the values from one temporary location, one relation to the another relation. So it is convenient at times to write a relational algebra expression by assigning the parts of its to the temporary relation variables. The assignment operation that is denoted by the arrow sign works like the assignment in programming language. So like we are using the flow lines for the assignment purpose, in the same way there is an assignment operation or operator that is used in a programming language. In the same way it is used in a relational algebra query. To illustrate this operation, to find out this operation, consider the definition of a natural join operation. That is, what is a natural join? So we can write the natural join, or we can assign or we can use the assignment operation, that is R, then there is a sign, then there is a S, that is a temp1 arrow R into S, that is the R is multiplied by the S and the output is placed in the temp1. In the same way, there is a selection operation, that is a select R dot A1 equals to S dot A1, R dot A2 equals to S dot A2, then so on till temp2 relation, that is all the variables, all the we can say the expressions are combined together and stored in the temp2 relation. Then result equals to pi R union S temp2. So this is simply assignment purpose, that is the output of this one will be assigned to the temp1. Output of this one that will be assigned to the temp2. So assignment is done by the arrow operators, that is known as the assignment operation. Next is the outer join operation, that is an extension of the join operation, or that is the advanced part of the join operation to deal with the missing information. So whatever the missing information that is available, that is filled by the join operation. Suppose that there is some instructor who teaches no course or no courses, then the tuple in the instructor relation for that particular instructor could not satisfy the condition of a natural join with the teacher's relation. For example, instructors Gulfi, Gold, Singh do not appear in the result of the natural join since they do not teach any course. More generally, some tuples in either or both the relations being joined may be lost in this way. The outer join operation works in a manner similar to the natural join operation that we already studied, but preserve those tuples that will be lost in a join or in a join by creating the tuples in the result containing null values. We can use the outer join operation to avoid the loss of, or to avoid this loss of information. What loss of information? That is the outer join operation. The left outer join operation takes all the tuple in the left relation that does not match with any tuple in the right relation. That is also available, and there is also a right outer join, there is a full outer join. There is a, first of all, there is a left outer join that is available, there is a right outer join that is available, there is a full outer join that is also available. That is, full means does both the right and the left outer join operations. That is, both the operations are followed, that is the left join and as well as the right outer joins. Then next is the extended relational algebra operations. That is the next topic. That is there are more relational algebra operation, that is more operation that is already available. So that is we can say the extended relational algebra operation that provides the ability to write the queries that cannot be expressed using the basic relational algebra operations. These operations are extended relational algebra operations. So these are not the basic operation, but these operations are the extended relational algebra operations. So first part is a generalized projection. That is the generalized projection. That is the first operation, which extends the operation, or which extends the projection operation by allowing operations such as arithmetic and string functions to be used in the projection list. So we use the projection list, we use the projection operation such as the arithmetic operation, such as the string operation, string function, that is to be used in the projection list. The generalized projection operation that has the form, this is the form, where E is any relational algebra expression, that is the E is any relational expression that is available, and each of the F1, F2 and Fn is an arithmetic operation that involves the constant and the attribute in the schema of the E. Then there is the aggregation. So one is the generalized projection, one is the aggregation. The second method is the aggregation, which permits the use of the aggregate functions such as min or average on the set of the values. Aggregate functions or aggregate function takes a collection of the values and return a single value as a result. For example, the aggregate functions sum takes a collection of the values and return the sum of the values. Therefore, the function sum applied on the collection that returns the value 24. So aggregate function means adding up all the values and give the results. This is also the, we can say, the example. Then next is the multi-set relational algebra. That is, what is a multi-set relational algebra, how the multi-set relational algebra is used. So unlike the relational algebra, SQL also allows the multiple copies of a tuple in an input relation as well in the query result. So just we have not done in the relational algebra, but SQL also allows a multiple copies of a tuple in an output relation, that is, sorry, in an input relation. So whatever the input relation that is available, so multiple copies of a tuple, or we can say the different copies of a tuple are available in an input relation as well as in a query result. The SQL standard defines how many copies of each tuple are there in the output of a query, that is how many tuples that is available in the query of each table. It depends in turn on how many copies of tuple are present in the input relation. To model the query or to model this behavior of a SQL, that is how to use the SQL, a version of the relation or relational algebra known as the multiset relational algebra is defined to work on the multisets. So there is a multiset relational algebra that is used to define on the multisets, that is a set that may contains the duplicate, that is the duplicate values are contained, that is defined in the multiset relational algebra. The basic operations in the multiset relational algebra are defined as follows. So this is a multiset operation, that is if there are C1 copies of T1 in the R1 and the T1 satisfied selection select n, then there are C1 copies of the T1 in the expression T0. For example, suppose that the relations R1 in the schema AB and the R2 with the schema C are the following subset. This is R1, this is R2. Then pi B R1 will be AA, whereas the pi B R2 into R2 will be A1 or A2, A2, A3, 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 A3. All tuples in the group have the same value. Tuples in the different group have a same or different values. Then next is the SQL and the relational algebra, that is what is the SQL and what is the relational algebra and what is the relationship between the SQL and the relational algebra. So from the comparison point of view of the relational algebra operations and the SQL operations, it should be clear that there is a close connection between the two. A typical SQL query has a form. This is a SQL query, that is select A1, A2, A1, AN from the R1, R2, Rm, where is a condition, where AI represents an attribute and R1 represents a relation. That is the same in the same way, that is equivalent to the multiset relational algebra expression. So this query, that is the SQL query, is very similar to the multiset relational algebra expression, that is a pi A1, A2, AN, and there is a select operation that is also used. So if the where clause is omitted, the predicate P is true. So if I miss the, we can say that if I miss the where clause that is omitted, then the predicate P is true, that is the permitted P means the permitted value of P is true. More complex SQL queries can be rewritten in a relational algebra. For example, this is the query that is given, that is a select A1, A2, A3 from table is equivalent to the A1, A2 G sum, then there is a pi, then A1, A2 till AN, then there is a R1, R2, R3. So join expression in the from clause can be written using equivalent join expression in the relational algebra. So this is the relationship between the SQL and the relational algebra queries. Now next is the tuple relational algebra. That is the next part. So we have covered with the relational algebra. We can say the relational query languages, relational algebra, that is a difference, union of multiple pairs. That is a we have finished. Now next is the tuple relational calculus, that is how to work with a tuple. What are the various benefits that is available with the tuple, that is the tuple relational calculus. So we are finished with the relational algebra. Next is the tuple relational calculus. This I'm not going to start right now because this is too lengthy topic and this is different topic and there is no student available. So that's all for today's session, and if there is any doubts, any confusions, you can ask the doubts from me. And so in the next class, that is in the Monday's class, I am taking your next topic. I am taking your next part, that is a tuple relational calculus. That is what is tuple relational calculus and how it is used in the SQL, or how it is used in the database to find out the various tuple, to find out the various rows that is available in the tuple relational calculus. So that's all for today's session. So thank you so much everyone for listening me, and if there is any doubts, any query, you can ask the doubts from me. So thanks a lot everyone. Bye bye.